Alright, lesson 1.6, inverse functions. Alright, let's get into the lesson. So let's say we have two functions, okay? The f function and the g function. How do we know if they are inverses of each other? Well, if you take f composed with g of x, and you get x, and if you take g composed with f of x, and you get x, then you know that the two functions are inverses of each other, okay? Let's take a look at an example of this. Alright, let me crop this real quick. Okay, so we have two functions here, the f function and g function. Okay, so if I want to know if these two functions are inverses, I need to check if f composed with g of x, is this going to give me x? Alright, so the g function, g of x, we know is cube root x plus 1 over 2. So I'm going to find f of cube root x plus 1 over 2. Okay, so g of x I know is equal to this, so I just write that in there. So to find f of cube root x plus 1 over 2, what this means is I need to take this, and in the f function, wherever there is an x, I'm going to replace it with this. So here's the f function, right? So we have 2 times x to the third. So instead of x to the third, I'm going to have this to the third power. So cube root x plus 1 over 2 to the third power minus 1. And then we work this out and see what we get. So well, we know the cube root and the cube right here, they cancel each other out. So we're going to end up with 2 times x plus 1 over 2 minus 1. Well, these 2's cancel, and then we get x plus 1 minus 1, and what do we get? We get x. Okay, so f composed with g of x gave you x. Right? Now, let's say you do this check and you don't even get x. Don't even bother checking g composed with f, okay? Because you need to get x, both times. So now we're going to do the other check. If we do g composed with f of x, this needs to result in x also. Let's see if it does. So f of x we know is 2x to the third minus 1. So f of x we know is 2x to the third minus 1. And then we need to take this, plug it into the g function. Okay, so let me do that. The g function right here is this big cube root. So wherever there's an x, I replace it with this. So we have 2x to the third minus 1 plus 1 over 2. Okay? Well, if I work all this out right here, I'm going to get the cube root of 2x to the third over 2, because the 2's cancel. Sorry, the 1's cancel. The 2's are going to cancel now, so we end up with the cube root of x to the third, which we know is x. So if you take f composed with g of x and you get x, and g composed with f of x and you also get x, then you know that these two functions are inverses of each other. Okay, so f of x and g of x here are inverses of each other. Okay, so you always need to get x back in return when you do these compositions. If you get anything else, they are not inverses. Okay, so if you do the first check and this isn't x, then don't even bother doing the second check. Okay, let's take a look at the graph of two functions that are inverses of each other. So here in gray we have a function, okay, y equals f of x. Here in black we have the inverse of this function. Okay, so this is the inverse. We are given that information. Now here's a relationship graphically between two functions that are inverses of each other. Let's say there's some point, all right, a, b on a function. Okay, that means that on the inverse of this function, right, there has to be the point ba, meaning the x and the y values will switch. So the x and the y values, the x and the y, right, will switch. Will switch for inverse. All right. And if you recall last year when I taught you how to find the inverse of a function algebraically, the first step we did was we would switch the x and the y, right? and this is the reason why. Because if AB is on a function, right, then on the inverse of that function, all right, the point BA must exist. Okay, it must exist. And what this means here is when two functions are inverses of each other, right, graphically they will reflect across the line y equals x. Remember the line y equals x, also known as the origin? Okay, so graphically they are a reflection of the graph of f in the line y equals x. Okay, so if two functions are inverses of each other, they will reflect across the line y equals x, which is also known as the origin. Alright, so if we take a look at the graphs of the example we just did at the beginning, g of x was the cube root of x plus 1 over 2, and f of x was equal to x 2x to the third minus 1. If you graph them here, you will notice that here's the line y equals x going through the origin. You'll notice that these graphs here are reflections of each other across the line y equals x. Okay, and we algebraically have already proven that these two functions are inverses of each other when we did their compositions. Right? Okay, let's talk about what a one-to-one function is. Okay, the formal definition is a function where every element of the range, remember the range are the y values, okay, of the function, corresponds to exactly one element of the domain, and the domain are the x values. Okay, so let me express this with this example down here. So first of all, over here you notice, remember to if a function, in order for it to be one-to-one, the x values cannot repeat. So you notice here this is a function because the x values don't repeat, right? So it is a function. But if you want to know if it's one-to-one function, right, you have to see if the x values, do they go to, all right, any specific y values more than once. You notice here these two x values, they both go to 5. Okay, that cannot happen for a function to be one-to-one, right? So the simple explanation is basically the two different x values cannot go to the same y value in the function. If it does that, it is not one-to-one. Over here, this function, right, it is a function because all the x values do not repeat, and each x value only goes to one's, all right, y value. All right, if all the x value goes to exactly one y value, then it is considered a one-to-one function. All right, then it's considered a one-to-one function. All right. So graphically over here, this is a function, right? Because it passes the, a parabola would pass the vertical line test. So we know it's a function. But is it a one-to-one function? Well, this point right here is x is 1, y is 1. Well, this point over here, x is -1, but y is also, all right, 1. So we have two different x's, right? Two different x's that go to the same y. So that means that this function here is not one-to-one. Okay, is not one-to-one. So if you think about it, what does this mean? This means that any graph that doesn't pass the horizontal line test, right? The horizontal line test. If it doesn't pass the horizontal line test, then it is not one-to-one. So if you have a function that doesn't pass the horizontal line test, it's not one-to-one. Okay? Okay, so why do we care if a function is one-to-one or not? Because to have an inverse function, a function must be one-to-one. Alright, so that's why we care if a function is one-to-one. So to have an inverse, a function must be one-to-one. Okay? So the definition of one-to-one, a function f is one-to-one if, for a and b in its domain, f of a is equal to f of b. Okay, and that implies that a is equal to b. This is used, I know this sounds really confusing, but this is used to check to see if, algebraically, if a function, all right, is one-to-one. Okay, and you'll see an example in a moment and it'll make a lot more sense. Okay, the existence of an inverse function. Okay, a function f has an inverse, all right, function f inverse if and only if it is one-to-one, and that's basically what we were talking about earlier over here. In order for a function to have an inverse, it must be one-to-one. Okay, a few special cases, all right, of functions that pass the horizontal line test are those that increase or decrease on their entire domain. Okay, so if you think about it, let's say we have the graph, a linear graph that just goes up like this, right? So here's the graph. It's going to pass the vertical line test, and then it's also going to pass the horizontal line test. All right, and you notice on its domain it just increases the whole time. Okay, so if you have a function and you know that on its entire domain it just increases the whole time, or on its entire domain it just decreases the whole time, then that function has to be one-to-one. Okay, it has to be one-to-one. Alright, so this is what you need to do in order to show algebraically if this function is one-to-one or not. You have to take set f of a equal to f of b, and at the end you need to see if you get a equals b. Alright, so let's do f of a here. So we need to do f of a. So f of a here. That means in the f function, wherever there's an x, we replace it with a. So we get the square root of a plus 1. Does that equal f of b? So in the same function, we're going to replace this with b, right? B plus 1. And if we start doing algebra, so we minus 1, right? We get the square root of a is equal to the square root of b. And then if we square both sides, right, we end up with a equals what? B. So if you end up with a equals b, that means that this function is one-to-one. Alright, it's one-to-one. Alright, so that's how you check algebraically. Just take the function, alright, set f of a equal to f of b, do the algebra, and then if you end up with a equals b, then it is a one-to-one function. So that's how you check algebraically. Alright? Okay, so graphically now, how do we know if a function is one-to-one? Okay, well, first of all, you always want to check to make sure whatever graph you get, it's a function in the first place. So in order for it to be a function, it has to pass the horizontal line test, right? I'm sorry, the vertical line test. So this passes vertical line test everywhere, and this also passes the vertical line test everywhere. So both of these are functions, but are they one-to-one functions? Well, in order to be one-to-one, they also have to pass the horizontal line test. So over here, hey, passes horizontal line test, passes horizontal line test, passes horizontal line test. Basically anywhere in this function, it's going to pass the horizontal line test. Over here, this function, even though it's a function, it's not one-to-one because it does not pass the horizontal line test. Okay, so it does not pass the horizontal line test. So basically, to sum this up, graphically, if you want to know if a function is one-to-one graphically, alright, one-to-one must pass vertical and horizontal line test. Okay, so if it passes vertical, it tells you it's a function. If it passes the horizontal line test also, then it tells you it's a function that's one-to-one. And what does it mean if it's one-to-one? That means that it has an inverse, right? That means that it has an inverse if it's one-to-one, right? Because not all functions have inverses. Okay, so let's take a look at the next example. So how do you find the inverse of a function algebraically, right? And we actually did this last year in Integrated 2 Enhanced. Okay, I'll just crop that. So you recall, if you're given a function and if you want to find its inverse, now remember, f of x we can always replace with y at any time. Okay, so the first step, when you want to find the inverse, you switch the x and the y, right? So then you're going to get x is equal to 5 minus 3y, right? And now you should understand why we switched the x and the y now, because remember, graphically, if two functions are inverses of each other, right, the x and the y values are going to switch on their graphs when they reflect across the line y equals x. Okay, so we switch to the x and the y, and then you have to solve for y, get y by itself. So you do whatever algebra you need to do to get y by itself. So we multiply by 2 here, get rid of that denominator. So 2x is equal to 5 minus 3y. Then we're going to minus 5. So we get 2x minus 5 is equal to negative 3y. And we divide by negative 3. So we know that 2x minus 5 divided by negative 3 is equal to, so instead of y here at the end, we replace it with the inverse notation, f inverse. Alright, that's how you would say this, f inverse, alright, the inverse of f of x. So f inverse is equal to 2x minus 5 divided by negative 3. So this function here would be the inverse of this function. So algebraically, that's how you would find the inverse. Okay. So let's take another look at another example of finding the inverse of a function algebraically. Okay. So we have a function here, f of x equals x to the third minus 4. So f of x is equal to x to the third minus 4. If we want to find the inverse of this, right, algebraically, you're going to first change the f of x. Remember, that's a y. And then we switch the x and the y. So x is going to equal y to the third minus 4. And then you get y by itself. So we're going to add 4 on both sides. And then we need to cube root. Remember, when you cube root both sides, you don't need the plus minus. So y is going to equal the cube root of x plus 4. And then we replace the y here with our inverse notation. F inverse is equal to the cube root of x plus 4. So this right here is the inverse of this function over here. Okay, so pretty easy to find the inverse algebraically. Alright? Okay, let's take a look at this idea here that's kind of interesting. We know that algebraically we can literally find the inverse of any function that we're given. For example, here we have y equals x squared, right? A parabola. If we want to find the inverse of this algebraically, it's actually really simple, right? So this is our f of x function, right? I've replaced the f of x with y already. If I want to find the inverse, well, I just switch the x and the y. And then to get y by itself, we're just going to square root both sides. I don't need that plus minus now. Right? And then so the inverse is going to be plus or minus square root x, right? So you might be saying, hey, you know, this x squared, y equals x squared, it does have an inverse. This is the inverse right here. All right? Algebraically, you can literally find the inverse of any function. But we know if we think about over here, x squared is a parabola. It doesn't pass the horizontal line test, right? Which means it's not one-to-one. If it's not one-to-one, that means that it doesn't have an inverse. But what's up with that? Because we just, over here, we just showed that, hey, we can find the inverse of this algebraically, okay? So in situations like this, what they will do is they will restrict the domain of a function so that you can include its inverse, okay? So what they'll say is for y is equal to x squared, the domain for it will be restricted, and they're going to say, hey, we're only going to count x is greater than or equal to 0, right? X is greater than or equal to 0, right, for the domain, because then it's only going to count this highlighted portion of the graph. Basically, this negative side over here, we are not going to include that, right, in our domain, so it's not going to include that part of the graph. So the domain is only this part here, from x going to infinity. So now, if we do the horizontal line test, it will pass, right, because we're only testing this part of the graph. So it will pass the horizontal line test, so it does have, alright, so it does have a, technically it does have an inverse, okay? So I know it's kind of a tricky idea, right? So in order for a function to have an inverse, it has to be one-to-one, right? So if it doesn't pass the horizontal line test, though, what they can do is they'll restrict the domain, saying, okay, the domain is only going to cover this much, and then these will be inverses of each other. Okay, so that's just a kind of a tricky idea.